So, dear colleagues, it's time to start, and I welcome you to the 229th seminar of the Moscow ACM Sigmod chapter. And our guest today is Antonio Rodriges from Higher School of Economics. So his talk will be devoted to the array database management systems, their problems, technologies, and future perspectives. And this talk is partially based on a tutorial which was given by Antonio on the last VLDB conference. And one remark concerning question and answers. This session will be arranged at the end of the talk and between the main parts of the talk. Am I right, Antonio?
Sure, thank you.
Okay, so Antonio, the floor is yours. Welcome.
Thank you for the invitation. So let me start my talk. So the talk is organized as follows. It will last for about an hour, and it consists of 5 main parts. The parts are relatively autonomous, so you can treat them independently. With the next slide, we'll continue the introduction. The remaining parts are devoted to array data models and query languages, array storage and tiling strategies, array indexing, as well as novel R&D direction. So the material is flavored with numerous promising R&D opportunities for future work. With this talk, we would like to increase awareness about this novel and exciting R&D direction, as well as to attract new researchers and inspire future work. We'll have a live Q&A session at the end of the talk and between the main parts. First, let me briefly introduce myself. I'm currently an associate professor at the Higher School of Economics, School of Software Engineering, Computer Science faculty. I carry out research and development in the area of array DBMS. I am the author of ChronosDB, which is up to 75 times faster than SciDB. So sorry, colleagues, someone has microphone unmuted. So thank you. Bitfun that tackles new type of array DBMS workloads, a novel R&D direction in the area of array DBMS presented at Sigmod last year, and WebArrayDB, the first array DBMS that runs entirely in a web browser. And most of those were presented at VLDB and Sigmod. The array DBMS history begins from Paradise and Titan, one of the first databases that specifically focused on array processing. To be more precise, the story begins from space. Sure, from space, a satellite was launched in 1981. As a payload, it carried advanced, very high-resolution radiometer. In 10 days, the radiometer could collect about 65 gigabytes of remote sensing imagery with the resolution of about 1 kilometer per pixel. At the time, this was considered a large data volume. What is more importantly, this data volume, its production speed, and the variety of query scenarios articulated the need for a data management system of a new category. It was quickly realized that many core data types in geobioinformatics, ecology, medicine, astronomy, to name a few, are naturally modeled by ND arrays. The next logical steps were general purpose array DBMS systems. Rastaman is one of the earliest array DBMSs, which is still active. But then we had a break. R&D in this area had been stalling. Meanwhile, much more remote sensors were launched into orbit. For example, Sentinels is a family of European satellite missions. About 203 terabytes of Sentinel products are disseminated daily. New data-generating devices and techniques appeared in physics, medicine, biology, and many other domains. In addition, this storage has become significantly cheaper. So, improved remote sensors, HPC simulation, cheap storage, and the resulting big array data avalanche has led to the renaissance of RDBMS R&D. So the last decade flourished with a significant number of groups carrying out R&D on array management. Of course, the most prominent systems are RDBMSs. Full-stack RDBMSs, they stand out by providing high-level end-to-end array management. For example, they provide query languages, execution techniques, and interoperability. Currently, there are only 3 operational RDBMSs to date. Array engines provide array processing APIs in diverse languages. For example, JavaScript, Scala, so are the main languages for Google Earth Engine and GeoTrellis respectively. Microsoft Planetary Computer was launched last year and is based on open source software. Then we can focus on relational DBMSs because they have specific add-ons which provide powerful capabilities on top of relational DBMSs. But they are usually tailored only to 2-dimensional arrays. National initiatives include Australian DataCube and European Earth Server. They feature complex analytic pipelines implemented using a broad range of software. Finally, array stores provide sophisticated array storage capabilities for specific workloads, for example, fast updates like TileDB. For example, Google Earth Engine is a prominent system, so it was launched on the 40th anniversary of the Lancet program, and it is the longest continuous space-based record of Earthland in existence, running from 1972 onwards. Another example is Maxar. It's a commercial company. Its former name is Digital Globe. It collects about 80 terabytes per day and accumulated over 120 petabytes of data in the Amazon cloud. And it's only one of the many companies. Advanced array management approaches are just emerging. For example, novel indexing techniques accelerate array joins and function evaluation. Compass can answer both query types, hyperslabbing and value selection. Bitfun tackles an important class of queries not explicitly considered before in the context of RDBMS, tunable queries. Only recently, top K queries, similarity joins, and so with different shapes and view maintenance were first introduced. These novel operations find their applications in many domains, including earth science, astronomy, and HPC simulations. Compression potentials are being explored. Researchers propose novel and efficient compression techniques. RDBMSs begin to support interactive visualization. Visualization is crucial for data understanding. It is provided by RDBMSs to avoid costly data movements to external visualization systems. Machine learning is just paving its way to RDBMSs. Hence, This whole direction has endless R&D opportunities. Novel research and development directions are opened in the area of RDBMS. For example, ChronosDB is the first RDBMS that can simulate the physical world. So with this, the part introduction is finished, and I would like to now move on to data models if you don't have any questions. If you do have questions, please unmute your microphone or type into the chat, and I will be happy to answer the questions. Okay, thank you. I don't see any questions in the chat and by voice. So let me move on to data models. RDBMS data models try to capture and generalize the diversity of big arrays. Time series, so this is a 1D array, two-dimensional geospatial grids, tracks, swaths, and other arrays where a dimension represents some coordinates, or time, height, model number, and so on. Three-dimensional spatio-temporal cubes like astronomical observations or biomedical data, unstructured meshes, and actually any data that can be modeled by multidimensional arrays. Arrays are traditionally stored in files, not in databases. Such files have complex naming, as you can see here, diverse coordinate systems, formats like netcdf, HDF, geotiff, supported data types, and so on. For example, the same data set may have very different storage layouts in different formats. It's also important that a data set almost always split into multiple files, like here with MODIS observations. The most widely used industry standard array data models are Unidata Common Data Model, GDAL data model, and ISO. So they're mappable to each other to some extent. All of them pursue the same main goal, provide a uniform access to a data type that can be provided in different storage formats or service APIs, for example, in the cloud. These models resulted from decades of considerable practical experience, but they share a key drawback. They work only with a single file and not with a set of files as a single array. However, a data set is usually split into multiple files. The ChronosDB data model formalizes and generalizes industrial experience. In addition, it treats arrays in multiple files arbitrarily distributed over cluster nodes as a single array. Moreover, it has a rich set of data types and supports multiple file formats with proper abstraction. These features are not simultaneously present in other data models, since GDAL, CDM, and other data models are mappable to ChronosDB data model. So let's cover this latter model, ChronosDB data model, in more detail. ChronosDB manages multi-dimensional arrays. An array has a name. It has a set of coordinate arrays and type T. Coordinate arrays can also have names like here, time, latitude, and longitude. Coordinate arrays enable modeling a wide variety of data types. A coordinate array maps indices to physical values. For example, one-dimensional coordinate array named latitude, is of type double, and has length 4. Its elements are degrees, latitude. Alternatively, it's possible to define an array just by its shape. A hyperslab here of an array is its ND subarray. We'll need these definitions in the future. The ChronosDB data model has 2 levels. At the first user level, the user perceives a large array as a single object, a set of system-level arrays, or subarrays, resides on cluster nodes, and they're stored as ordinary files in diverse file formats. An operation with an array is mapped to a sequence of operations with respective subarrays. In this example, array A resides on 3 cluster nodes. So the subarrays are colored in red, green, and blue. And this marks the node, different cluster node. And subarrays are separated by hyperplanes and are referred to by keys. For example, we refer to this highlighted subarrays by the key -1, 0, and 1. This is the example of a ChronosDB array and its schema for real-world data. So red rectangles in this image, and so in the figure are subarrays, and they're logically presented to a user as a single large array. The ChronosDB gdel-info command prints array schema, as you can see here. The meaning of the fields in this schema and this output is the same as for the well-known gdel-info tool from the gdel package. And this gdel-info tool, it handles only one file at a time. On the contrary, so here gdel-info prints the information, the schema for a very large array consisting of subarrays. Because gdel-info is quite popular, most users avoid learning a new array schema notation, and they can inspect ChronosDB arrays in a way they're accustomed to. So let us take the real-world data set from the previous slide, and we would like to compute a popular vegetation index, which is called NDVI. It takes two two-dimensional arrays as input and produces a two-dimensional array as an output. This is a typical map algebra operation, as you can see here in the map algebra notation. So this operation is represented by this formula. So array query languages greatly differ between array DBMSs. Currently, there is no well-established standard yet. ChronosDB users work with a system as if they are already familiar with command line tools. ChronosDB commands have the same names, the same syntax, and even the same options as well-known command line tools, for example, gdel-calc. Hence, users can start working with ChronosDB immediately and avoid learning a new language. RASDMAN, a query language, which is RASQL, strives to be similar to standard SQL, but some queries may look unusual for an SQL user. So, and this example is at the bottom. For example, this syntax, very large syntax, tells Rassmann to compute max over a 3-dimensional array. So SciDB is equipped with array functional language, and this language has a set of operators in the functional style. Nesting is used to feed the output of an operator to another operator. So this forms, as you can see, long chains. Here, apply, it takes an array produced by join, and so store here, so at the top, it materializes the resulting attribute extracted by project, actually NDVI. PostGIS, so it's a well-known tool, and unfortunately, it's tailored to 2-dimensional arrays. It provides a lot of functions which can be called from pure SQL, and PostGIS users work with a set of independent 2D tiles not treated as a single array. Users must explicitly seek intersecting tiles and properly organize the computations, which is quite tricky. Here, predefined UDF computes NDVI. R&D-DBMS data models are at their early stages, so they largely focus on numeric arrays and largely omit other important data types, including polygons, tables, graphs, and we have a lot of challenges related to this approach. So nowadays, a key meta challenge is the joint processing of diverse data types within a single system, R&D-DBMS. So let me showcase several promising R&D opportunities. One of the ways to solve the challenge is the algorithmic way. As an example, consider Raptor to compute zonal statistics, so like average of raster values inside a given polygon. Existing systems rasterize a polygon or perform expensive point-in-polygon lookup queries. So both approaches are time-consuming. Raptor uses scan lines, as you can see here, with a step equal to the cell size. It quickly computes the range of indices from min to max that contribute to the result. However, Raptor is designed for zonal statistics, so this challenge requires more operations and more algorithms. Polystore systems tackle the challenge in another way. They do consider R&D-DBMSs, as you can see here. SciDB is an example. But they underutilize them. For example, geospatial, bioinformatics, astronomical, and other array-intensive workloads have been not extensively studied in polystores. So I encourage you to explore this interesting direction. Next, another interesting R&D opportunity is working with graphs inside R&D-DBMSs. So R&D-DBMSs can potentially model graphs and tuples as arrays, but we didn't extensively evaluate that. We would like to keep users within a single system during array-intensive workloads. Otherwise, we miss both users and optimization opportunities. Modern R&D-DBMSs do not implement graph algorithms and hardly optimize for computations on sparse arrays. Recent work explores graph and relational workloads on tensor computing systems like PyTorch with very high interest. RDBMSs have an exciting opportunity to join this novel trend. So thank you with this. This part is over. And before I switch to the next part of my talk, so let me check, are there any questions?
Okay, dear colleagues, do we have questions?
I got one question. Could I ask it?
Yeah, sure.
Sure.
About 25 years ago, I think Elasta object relational database management system was introduced, as well as Informix Universal Server and I think Oracle Universal Server. These technologies were based on typical SQL servers, but data types, basic data types, were allowed to be complex data types. And for example, there were it was possible to implement traditional relational database without first normal form, when cell of the item was an array or special data. So my question is, did you compare array DBMSs with object relational DBMSs which supported arrays as the basic types?
So thank you for your question. And this is very important question. Actually, in this talk, I will not emphasize this challenge, this R&D opportunity. However, in my tutorial, you can find a very acute need for such comparisons. Actually, currently, there are too few comparisons of array DBMSs so for different workloads, and this is one of the great R&D opportunities. Actually, so as far as I know, so the comparisons of such type, so such kinds are lacking. So, and it would be very great. So, for example, if you are experienced in these databases, like you said, Informix and some Oracle, if the license, of course, permits that. So it would be great if you join and compare. So the performance of these systems against array DBMSs. So it would be great. But I think the paper could be very solid if you will undertake this great job, so this comparison.
Thank you. Do we have more questions? So in this case, I do have several questions. So Antonio, could you please return to this slide with query languages?
Sure.
So concerning SciDB, for instance, as I know, SciDB, besides this functional style language, implements also declarative style language, AQL.
So sure, it stands for Array Query Language.
Yeah, Array Query Language. Yeah. And okay, maybe from your point of view, what is more perspective? What language is more perspective as a query language for array databases? From my point of view, I do like declarative languages, SQL-like languages, like for numerous databases, like graph databases and array databases. But here on your slide, we see that you propose in Kronos DB, you propose a command line interface, which is very close for the usual tools used by people in earth sciences, for instance. And you also mentioned the functional languages, but it seems that it's not the main point of your investigations to implement declarative languages.
So thank you for the question. Some comments. So according to the documentation of SciDB, it so does implement so this AQL, array query language, but they note that so it so much more limited than AFL, array functional language. Actually, they don't support the same set of capabilities and the same set of functionality as the array functional language. Actually, this doesn't mean that that language, AQL or AFL, is better or it's more convenient for some people and it suits some particular purposes. This simply means that their work is not finished. And here, Kronos DB, because so the main data sources were geospatial arrays, and that was logical to equip users with well-known tools and to avoid learning from scratch. And again, this doesn't mean that this language suits better for array DBMSs. And actually, currently, there are no standards. So Rasdeman tried to propose a standard, but actually it so didn't receive wide adoption. And I think so that personally, that we will have a lot of, so at least 2-3 popular languages for array DBMSs in the future. This is not just because of the nature of array DBMSs. This is also because of the general trend in the databases. Because recently we can see the shift towards polystores and towards polyglot systems which support multiple languages, which support APIs, which combine different libraries. So SciDB, for example, started to support Python UDFs. So and as components, array DBMSs also can be used in these polystores. And so considering this trend of polystores and polyglots, I think every language will have its right to exist. So, and I think we may even have more languages in the future, not just, this is not a limitation, these 4 languages, because diverse workloads from people come from bioinformatics, they prefer their languages. Other people come from physics, they were accustomed to that language. So this is very good question, and again, no good or bad language. Most DBMSs, array DBMSs, will support several languages.
Okay, thank you a lot. And maybe just another question concerning this part. So you mentioned that the important direction is integrating heterogeneous data from different data models, and you also mentioned one possible way, polystore way. And do you have in mind another option, which is called multimodel databases? For instance, we do know a lot of variants for multimodal databases supporting relational and graph databases as in a very integrated way. So do you have in mind such an option for array DBMS? And what is the most prospective companion for array DBMS to be another data model to be implemented in multimodal database management system?
Well, thank you very much for the question. Actually, the work is in progress, and I think the work so in different directions happens currently in parallel. The most prospective, two most prospective directions, I think, if you're interested, what should be the next? This is probably relational tables and graphs. And actually, there is quite a large volume of ongoing work which already integrates these relational tables into so-called array stores. However, I would probably even mention here, sure, at VLDB 2021, if you look at this paper, so tensors, an abstraction for general data processing, this team, so from ETH Zurich, they used arrays, and they put relational data into arrays, and they reported so quite promising results of using arrays. And if you look at some different papers, for example, here, Graph Blast, so they, as the next step, they focus on graphs again, because this is a very important abstraction for spatial networks, for social systems, for relations. And again, if we use arrays, if we use linear algebra, and if we use vectorization, if we use GPUs, we can see quite significant speed up. But still, the problem remains of elegantly having all these types in a single system. So what should be the language? What are the deviations from the standard SQL language? So, but the work again is going, right? As you can see, you can look at quite recent papers, and I think we will see a lot of progress in the near future of accelerating our DBMS queries and graph workloads.
Okay, thank you.
So do you have any questions? So if there are no questions, so let me continue to array storage. So the next section is devoted to array storage and tiling strategies. So we are going to cover database and file-based approaches, and we also mention several attractive and promising R&D opportunities. Before we continue, so let's revise chunking. So chunking partitions an array into a set of I/O units called chunks. Chunking is an approach to substantially accelerate I/O. So what is the best chunk shape? Consider an example. Given an array of 12 by 12 cells, the task is pretty simple. We need to read a 6 by 2 subarray from the given array. Without chunking, we need 6 IO requests to complete the operation. We can chunk the array, so like this, for example. However, the situation gets worse, as now we read half or 50% of all the data, right? Because a chunk is an IO unit. A better chunking would be similar to the case C. We still do only 2 IO requests like here, so we read almost exactly the array portion we need. So, and this is only one example. The trick is that the best chunk shape depends on the workload, which you do not generally know a priori. Moreover, the workload can change dynamically. Chunk shape is a crucial performance parameter. For different chunk shapes, the performance of SciDB differs by orders of magnitude, as you can see here. In addition, there is no best chunking scheme for all workloads. As you can see, the extraction of a time series runs the fastest on chunk shape, so here D, right? 0.6 compared to 104. So this is a very significant difference. Hence, an array DBMS must be able to quickly alter chunk shape. Suppose an array DBMS workload changed. Now you need to chunk your array to a shape that better suits the workload. Kronos DB is up to 1,000 times faster than SciDB for the chunking operation. Please choose the right database for your tasks. Almost all array DBMSs or array storage systems utilize chunking. Kronos DB keeps data in diverse file formats, and so Kronos DB and SciDB, they use regular chunking. TileDB operates on data tiles that have the same number of non-empty cells to facilitate load balancing. Rasterman stores array tiles in blobs and provides 4 tiling strategies. These are regular used by most systems. So chunking, right? Irregular, partially aligned, and totally non-aligned. So this is the chunking strategy supported by Rasterman. The documentation gives some hints on what strategy to use, but it's up to users to pick up a strategy and its parameters for better performance. So Array Store investigated tiling techniques for clustering, slicing, and other workloads. They also use 2-level tiling strategies, both for regular and irregular. They conclude that a 2-level regular tiling workloads is best for workloads they tested. TileDB targets multiple cell-wise random writes in batches to different array regions and fast reads of the resulting array. TileDB writes data in fragments, as you can see here on the left, timestamp snapshots of a batch of array updates. An unempty cell from a newer fragment, it overwrites a non-empty cell from an older fragment. The core idea behind TileDB is as follows. A fragment can be represented as a set of 1D segments or 1D arrays. TileDB sorts these fragments by timestamps. Here, this is the time axis, and intersects them and reads only the newest updates. For example, two latest segments overlap and they're updated the same region. TileDB will discard some values here from the second fragment as they are outdated. So what are the R&D opportunities? Nowadays, chunk shapes are mostly hand-tuned experimentally by R&D-DBMS users. This is surprisingly. Research literature proposes some automatic chunking strategies, but they didn't find their way into R&D-DBMSs. So hence, we need novel, more general heuristics for automatic selection of proper chunk shapes, especially in runtime for interim arrays, as users don't control their shapes. They control only the shapes of input arrays and output arrays. But what happens to interim arrays? Here we are free to select chunk shapes. What about file-based approaches? R&D-DBMSs serve diverse scientific communities that collected and processed array data for decades before R&D-DBMSs appeared. Terabytes of array data are collected and generated daily. Hence, arrays natively come in diverse file formats, including NetCDF, HDF, GeoTIFF, and hundreds of other file formats. Novel in-database storage approaches require time-consuming data import phase. However, arrays natively come in diverse file formats, HDF, NetCDF, GeoTIFF, and others. Moreover, arrays are also shared in established file formats. So because they're standardized, they're open, so users prefer to share them in these standardized file formats. In addition, update workloads are currently rare in many application domains. So even this paper states that scientists require no override storage manager. A closer look at popular file formats reveal that they're like small databases. For example, GeoTIFF represents an effort by over 160 different companies and organizations. So, and it has a lot of capabilities, including overviews, that is array instantiations for multiple zoom levels, tiling, varying number of bits per cell, they support large and sparse arrays, and so on. So the natural question is, why not to use these powerful file containers directly as a storage layer of an array database? That's exactly what ChronosDB is doing. Its storage layer is based on established, standardized file formats. Files are distributed among cluster nodes and processed in parallel. The ChronosDB data model, it abstracts from the files and treats all related files as a single large array. Unlike other DBMSs, ChronosDB omits the time-consuming import phase. ChronosDB immediately gets powerful storage capabilities that include storing diverse data types, efficient missing values support, and numerous compression techniques out of the box. Moreover, ChronosDB arrays are readily accessible to any other software as a set of ordinary files. For example, geographic information systems, R, Python, and many other software that can read such files. So another important R&D opportunities include sparse layouts for existing file formats. Nowadays, established file formats like HDF5 are being adapted for storing sparse arrays. Again, this is not simple. We have a very solid code base, and the key challenge here is not to introduce breaking changes to an existing API. Most such work is just commencing. In addition, recall that there are hundreds of array formats. For example, GDAL supports over 100 drivers, and you can always design your own, for example, for specific workload or applications. Thank you for listening. So I finished this part. So, and if you have questions, I'm happy to answer.
Okay, do we have questions right here? I do not see any questions by now, but okay, I had some questions concerning sparse and dense arrays and the issues of their storage, but you almost answered all my questions before I had a chance to ask them. But okay, maybe just one question. That according to your experience, what are the most popular problems over what form of data, over sparse arrays or over dense arrays? Because concerning my knowledge in multidimensional models for online analytical processing, so mostly data cubes with high number of dimensions are very sparse. And what is what is the current situation in your field, in the field of problem solving over array data?
So thank you for the question. Indeed, so we have two types of arrays, sparse and dense, and currently a lot of techniques and a lot of algorithms were designed to store dense arrays. And currently, the most challenging problems we have are in sparse arrays. This doesn't mean so we don't have challenges in dense arrays. So the next part, for example, array indexing will show you a lot of challenges. But the trick is that here in array databases that we try to serve many diverse communities. And in some communities, dense arrays, so quite often so are the only type of arrays. For example, in geospatial data and satellite imagery, in unmanned aerial vehicles, but in bioinformatics, for example, they have mostly sparse arrays and they almost never use dense arrays. And again, because of this diversity of fields, the work is going in parallel. So there are groups that develop sophisticated storage and processing techniques for sparse arrays, and the other groups are developing sophisticated indexing, as I will show you just in several minutes, for dense arrays. And again, the problems still emerging in both types of arrays. And the key inspiration for all these problems are workloads from diverse communities. For example, if I have a technique for storing sparse arrays for bioinformatics, and if it is successful, it's usually quite hard to generalize such technique and to say, okay, I will use these sparse techniques in other domains. So in array databases, we must, so to date, right, we must always account for the domain. Because when we develop some technique, we usually, not always, but usually, so take inspiration from some applications, from some real world applications. Of course, there are some fundamental problems, for example, array joins. I will not mention it today, but as an example, there are algorithms that try to treat sparse arrays in all domains. So something like that.
Okay, thank you a lot. Do we have more questions concerning array storage right now? Okay, I do not see any questions.
Okay, thank you for your question. So let me continue. So, and this is the array indexing section, and I invite you to discuss array indexing. And regarding the questions from the previous section, now you will see that we do have a lot of challenges for all types of arrays. And here, so I will present some of them that are related to dense arrays. As you can see, we have a lot of interesting problems also in dense arrays. However, at a glance, one may say, okay, we have a lot of formats, we have a lot of storage techniques, we have a lot of algorithms for dense arrays. So what should we do here? What can we achieve in this area, right, in dense arrays? But there is a lot of work here and a lot of promising directions. So state-of-the-art array DBMS index types fall into three categories. The first is cell value selection. So cell value selection indices accelerate seeking cells whose values are in a given value range, like here. For example, select cells with values greater or equal to 3. Compute indices accelerate computations on arrays. For example, compute a function, slightly tune the parameter, the input parameter, and compute the same function again. Tune the parameters and compute again, and so on. So hyperslabbing indices accelerate seeking cells in a given spatial range. See, they use relatively well-known data structures, so we're going to focus on the first two categories. Consider the following real-world example. The query is to find cells with wind speed greater than 20 meters per second. It's obvious that the resulting cells constitute only a small fraction of this array compared to the whole array volume. Hence, we should not perform full array scan when we answer such range queries. Bitmap indices utilize three main techniques: binning, encoding, and compression. Usually bitmaps have good compression ratios, so this makes them especially efficient. First, cell values undergo binning. In this example, a set of floating point values are divided into 3 bins. After that, bin numbers are encoded as bitmaps. Equality encoding creates a bitmap for each bin. The bit in a given position is set to 1 if the cell with this position in the original array has a value belonging to the bin number associated with the bitmap. It is good for equality queries shown on the slide, like here. You read only the bitmaps for certain bins and perform bitwise operations. Range encoding is well suited for one-sided range queries, like here, while interval encoding this example is well suited for one-sided range queries. So, sorry, for two-sided range queries. However, bitmap indexing has a drawback. So for array DBMSs, you know that a chunk is an I/O unit. We need to read a chunk completely, which may be up to several megabytes, and even only if a single cell contributes to the result. In this example, as you can see, almost all chunks contain the cells, so which contribute to the resulting query. And actually, we need to read almost the whole array, which is not good. And integrated value index mitigates the aforementioned drawback. The array is still accessed in the granularity of chunks. However, each chunk contains subchunks. Consider the example on the slide. The array is divided into 6 by 6 chunks, like here, right? And each chunk of 5 is a 5 by 5 cells is further divided into half open buckets with an interval of 1, right? So here 1, 2, 2, 3, 3, 4, interval of 1. For each bucket, a bitmap indicates the position of cells inside the chunk. So, and we have a segment of residuals that keep the trailing bits of the values. The index is optimized for both hyperslabbing and value-based queries. So a query examines only chunks intersecting the query region, right? And reads the whole chunk or just buckets in the queried value range. You need to create a full logical copy of the original data if you would like to use this indexing technique. The storage footprint, that is the percent of the uncompressed data set, the last column here, is always less than 100. A peculiar feature is that chunks should be very large, for example, 64 megabytes, in contrast to usual sizes of 4 to 8 megabytes. So you must have very large arrays. In addition, indexing params for a given workload may be not straightforward to obtain. So let's look at a query example with a tunable function. So as you can see, in both examples, we discuss dense arrays, and we have very interesting solutions for novel types of queries or existing queries, but which are optimized. As input here for a query with a tunable function, we take two large 2D arrays storing intensities of reflected solar radiation, near infrared spectrum and R-red spectrum. As output, we get a large 2D array, soil-adjusted vegetation index, so which aims to minimize soil brightness influences. This function is special. This is because it includes a tunable parameter, so whose value is not known in advance. We may tune L many times to find an appropriate value, and it's very time-consuming to recompute this from scratch. In practice, SAVI can be used to predict crop yield according to the recent publication. However, we need to recalculate the crop yield each time we tune L. SAVI is not alone. Dozens of math functions with tunable parameters are used in practice. Array DBMSs answer queries with tunable functions as follows. For the first query, we get some L, and compute SAVI from scratch. Next, we slightly tune L and submit this SAVI query again. However, SAVI is computed from scratch again. This repeats for each subsequent query, regardless of whether we computed SAVI before or not. Bitfun computes SAVI from scratch and creates an index. During the second query, Bitfun doesn't compute SAVI from scratch, but uses the index to answer the query. Bitfun tackles an important class of queries not considered before in the context of RDBMS, tunable queries. So Bitfun explicitly focuses on the fact of tunability. Let me share some insights. Please have a look at this SAVI function. In general, it's rather a non-trivial function. However, we need only a particular piece of this function. Now a natural question arises. How significantly does SAVI value change when recomputed for L plus a small delta? Let's fix near and R values. Now SAVI becomes a function of only one variable. This is L. If we look even closer, we will notice that SAVI is close to a line in the vast majority of cases. This is for most combinations of near and R values. So wondering what if the function is not a line? Please have a look at the paper for more details. The Bitfun approach from a bird's eye view looks as follows. So the Bitfun index contains identifiers of simpler functions approximating the given function with the required precision. Real data is not random, so the number of approximating functions is typically small. The indexes have good compression ratios. Bitfun can answer three query types, namely compute values, function values, evaluate inequality, and perform classification. Bitfun is integrated into ChronosDB. You can find more at the Bitfun homepage. Without Bitfun, you read two large arrays each time you recompute a function. With Bitfun, you read only one compressed array. So this enables Bitfun to answer queries up to 8 times faster. Until recently, so the research in array storage focused on persistent arrays. Recent research reveals that specialized formats for interim arrays like Bitfun and Compass can vastly reduce I/O and save CPU time. This research direction is very young, so please have a look at the publication years of the papers. Hence, many exciting opportunities are to be explored. So, and these both techniques, as you can see, they significantly accelerate operations on dense arrays. So we have a lot to do, and a lot to improve in these types of arrays. So thank you. With this, the section of array indexing is over. And if you have questions, I would be happy to answer.
So, dear colleagues, do we have questions concerning this part? Okay, I just comment this that these tunable queries, well, it's quite fun to see these ideas, but maybe the question is, well, again, concerning your experience. So your approach is suitable for what range of possible functions?
Well, currently, and in the paper, we considered one type of functions. And these functions had only one parameter.
Okay.
Well, in the future, this is the challenge to account also for other types of functions.
Okay, I see. Thanks a lot. Do we have more questions? Okay, I do not see more questions right now.
Okay, thank you. So, and this is the last part of the talk, and it's devoted to novel research and development directions in the area of array DBMS. So, let me present one of the novel research and development directions in the area of array DBMS that opens a wide range of promising research opportunities. Array DBMSs manage big multidimensional array storage, processing, and even visualization in some cases. Physical simulations have been traditionally implemented on diverse types of grids and meshes that can be modeled as ND arrays. As multidimensional arrays are at the core of array DBMS, it's logical to apply array DBMSs to physical simulations to benefit from array DBMS capabilities. Cellular automata seem to be a good starting point for integrating simulation into array DBMS. This is because they have multidimensional array models for their lattices and numerous successful applications, as you can see here, for fire spread modeling, land cover change, road traffic simulations, and many others. We solved multiple design challenges to enable cellular automata simulations possible inside array DBMS related to iterative workloads, cellular automata transition rules, parallel execution, and other challenges. A database approach to physical simulations brings numerous benefits. Let's take ChronosDB as an example. It enables automatic parallelization, easy debugging, DBMS-like data management, and interactive visualization, to name a few. Currently, only ChronosDB supports both end-to-end parallel cellular automata simulations and DBMS-like simulation data management. If you perform simulations, you will always need to manage your input and output data, share and visualize your results. In general, you are more productive if you can use only one system rather than a lot of systems from which you import-export your data. And only one system will help you to more productively accomplish all your goals, and so quickly and easily without data migration. As an example, we constructed a complex road traffic cellular automaton based on the literature with multiple lanes, road intersections, traffic lights, different vehicles lengths, varying vehicles speeds, and complex vehicles behavior. We took a traditional traffic cellular automaton grid that's used for in the state-of-the-art research, an artificial road map resembling Manhattan grid, New York City. Let's showcase one of the benefits of running the simulations inside array DBMS. ChronosDB provides array imagery via an open, popular web mapping protocol. This is WMTS, Web map tile service. Hence, users can watch the modeling at work on an interactive web map, how vehicles move along the roads, how they queue at traffic lights, how they turn at road crossings, so accelerate, brake, change lanes, and overtake each other. To our best knowledge, our work is the first to run end-to-end cellular automata simulations completely inside RDBMS. We enable RDBMS to simulate the physical world for the first time. Please learn more at the paper homepage you see at the bottom left. Another interesting and novel research and development direction is related to web geographic information systems and array DBMSs. So as you know, web browsers are becoming increasingly popular platforms for client applications. Web GISs, this is geographic information systems. And modern web GISs run all array processing on the server side, for example, in the cloud. They use geospatial protocols to send queries and retrieve images for display, for example, PNG files. This increases response times, degrading the user experience, especially for tunable queries. So we showcase WebArrayDB, the first geospatial ArrayDBMS that can run completely inside a web browser. Rodriges is our new WebGIS based on WebArrayDB. A web-based ArrayDBMS should reduce server load, enable offline work, decrease network I/O, and improve user experience. Modern web browsers are sufficiently mature to run a powerful ArrayDBMS. WebArrayDB ingests raw data, currently GeoTIFFs, via a popular web protocol. The storage engine relies on a JavaScript API for storing significant amounts of structured data in a web browser. WebArrayDB uses an SQL-like query syntax. To parse queries, we use a purely JavaScript library for symbolic computations. As you can see from this chart, ArrayGIS can be over 2 times faster compared to querying on the Sentinel Hub, which is a popular cloud service for providing satellite data. ArrayGIS is freely available at WebDB GSGG, so please check the paper to go through interactive lessons related to real-world tasks on multispectral satellite imagery. So let me briefly mention the most promising R&D opportunities for this part of the talk. For RDBMSs, novel applications are the major drivers for innovations. Diverse scientific communities collected and processed array data for a long time before RDBMSs appeared. If we would like to add value, we immediately discover many unexplored RDBMS applications that are a fruitful ground for new data management challenges. If you would like to know more, you can refer to lecture or tutorial that was held at VLDB 2021. So for 1.5 hours, and it was in the main program day and main conference day. At VLDB 2021, only 8 tutorials were accepted. So, and the tutorial was in a separate section. So thank you for your attention. Thank you for listening, and I'm happy to answer the questions.
Okay, thank you a lot for your talk. So, dear colleagues, do we have More questions to Antonio? Oh, okay, maybe I do have one more question, but well, and maybe it concerns possible implementation of machine learning methods over array databases. Do you know something about this direction? Because we do know about these implementation over relational databases, and do we really need such tools or such methods to implement these machine learning methods right into the array database management systems?
So thank you for the question. Very interesting and very important question. And the answer to this question is, for 100% sure, we do need these implementations inside array DBMSs, because we would like to avoid costly data migrations between different systems. And there are some implementations. However, machine learning is just paving its way to array DBMSs. And in this tutorial, you can find a paper if you visit this link, and you can find some video that introduces some machine learning implementations. However, they're still basic. For example, there are experimentations with linear regressions and matrix multiplications. And we have a lot of work to do here. And actually, machine learning is one of the most promising research and development directions, because most things are not implemented, right? If you do something, you will be probably, with a high probability, the first in this direction.
Okay, thank you a lot. So, do we have more questions? Yes. Roman?
I have one question. As we started talking about NLP, machine learning area, so close to that there is NLP. And in NLP there is issue, a big problem, how to find similar points if you are talking about vector space and embeddings. So that is a little bit different compared with array DBMS, but if you are talking about representation of embeddings, so you have a huge space of vectors. And the main issue, how to find the nearest points. But at the same time, if we are talking about the nearest points, so the way how to resolve it, it's a little bit different compared with presented in this talk indices, like hierarchical approximate indices. But at the same time, sometimes you have tasks like clusterization points of those multidimensional points and embeddings or something like that one. So it is interesting how to intersect that, or do we need to keep it different like array database management systems and separately keep vector-based search machines, or do we need to intersect them? So any comments?
Thank you for your question. Again, very interesting question. So I think we should try everything, right? And we should pick so that works best. And I think the future work will definitely have some solutions that both have some intersections, and for those that have different systems, so for the problem you just described. And I think this is research, and interested researchers will do their best at optimizing the problem. And as you know, many papers combine the best of several worlds, or they arrive at some new solutions. So here we must not restrict ourselves to some particular systems or existing solutions. I think we must do what we need to do research and try different workloads and look so what best suits these workloads. So, and we must start from certain database. We must look, for example, whether the data can be easily ingested into these database. Okay, if it's easy, if it's not, can we do some modifications to RDBMS, for example, to make it easier to ingest the data? Okay, if we ingested the data, so let's look. So which techniques currently in RDBMSs we have, so which can facilitate in solving this problem? Probably, so the solution will not be faster as state of the art, right? So probably you can find systems that can do better. But if from the point of view of the industry or from research perspective, if there is some interest, if there is some benefit, okay, we can continue in this direction, and it will be the matter of time. So whether we will get a solution that overtakes state of the art somehow. So very interesting direction from my point of view.
Thank you a lot. So do we have more questions?
Again, when we talk about DBMS, we usually talk about transactions. It seems that most applications that use RDB should use read-only mode, not OLTP mode. Is it correct?
So thank you for your question. Today we covered, for example, SciDB and TileDB, and they're not read-only, they're optimized for write-intensive operations, and they can mix read and write operations. So both database types exist. So which read optimized and which are write optimized, and both research directions again exist. For example, which so let me show you this slide. Here it is, TileDB. If we're so speaking about TileDB, as you can see, it is write optimized. You have a lot of writes, you have a lot of fragments, and so the task is to quickly read so the up-to-date version of the array. And so many types of databases exist. Not all array databases are read optimized, and not all array databases are write optimized. So is that what you expected or something else?
Thank you.
Thank you.
Okay, thank you a lot. So I think we should thank Antonio again for quite interesting talk, for review of methods and solutions in the area, and also for presentation of his own results in this area that are quite impressive. So thank you a lot.
Thank you
for being our guest here.
Thank you.
So
Thank you. Thank you.
See you next time on our seminar, I hope.
Thank you.
So
goodbye.
Bye.